Oh man, we're streaming again. Welcome back. This one should be pretty interesting. We're still working on that gimbal, but a couple of neat areas of progress. We actually have some firmware to take a look at, and I have a little UI tool that makes it easier to mess with the parameters. Oh man, the fluff tiger. So yeah, welcome back to the stream, folks. Let's start this off with a little bit of cat, since of course he's being super cute. Of course, the high-level goal of this particular project, at least, is to have a robot that makes it easier to interact with this lovable, adorable cat via the internet. So that's the most important goal here. But then, in order to have a more interactive camera here, other than this little tripod, we're planning on making a robot that flies around on cords and carries a gimbal that points a kind of HD closed-circuit TV camera at my cat here under control of, hopefully, Twitch chat. So, that's kind of the first couple steps here. So we're working on a robot to give my cat some internet interactivity, and the robot has a gimbal, and I was modifying the gimbal, and during that process, both wanted to have some more control over the gimbal so that I could point it without having these pulse width modulation inputs and with an absolute control over the angle. And I kind of broke the parameter set such that I needed to either recalibrate it or reset the parameters somehow. So that combination of things has caused this gimbal investigation to deepen. So now we're at this point where we have parameters that we can mess with in the gimbal. I have the protocol figured out enough that we can set and get parameters while the gimbal's operating, and I have some idea of what those parameters are. There's still a lot of unknowns there, and we still need to figure out how to tune the gimbal well enough that it doesn't wobble as it moves around. It's almost usable. I'll show you the state that it's at right now. Are we not online yet? Oh no. Is it not actually streaming? Oh no, maybe it is live. I just had to reload the page over here. Okay, cool. So sorry for the interruption there. So just kind of recapping where we are. We've got this gimbal. It had this confluence of both kind of an opportunity and a problem, where I wanted to try to gain more direct control over the angle the gimbal was pointing at, rather than having to emulate these RC control joystick signals that weren't quite what I wanted. And in the process of doing that, I broke the parameter set such that I needed to go back and fix it. So I had multiple reasons to need to dig deeper. So at this point, we have the protocol figured out, at least enough of it to get and set parameters and to write them to flash memory and to turn on and off the motors. And I think I know how to send basically the serial port equivalent of joystick position updates. I just haven't been able to get the gimbal into a state where it seems to want to do much with those inputs. So that might be something we explore too. So part of this is using that protocol to actually try to fix the parameters that are broken. So I've been trying to build a little bit of UI on top of that raw protocol implementation in Python, just so that we can actually graph the parameters that we have, set the parameters interactively, because with the control system that's basically a bunch of interdependent variables, a lot of them three-dimensional vectors, it's really annoying to just try to deal with this completely from the console. So I had started to work on making a better UI using Jupyter / IPython notebooks. So with IPython notebooks, you can easily interact with Python code, and I was getting some mileage out of this by using the IPython widgets, like the sliders, to interact with parameters in real time. But all of my experiments in trying to graph results in real time using IPython widgets, that wasn't really successful. I tried some new matplotlib backends, and it still wasn't nearly fast enough. So I switched gears and I built a different parameter UI using plain old HTML5 and an existing JavaScript plotting library called smoothie charts. And using that and WebSockets, I was actually able to make something that's pretty fun to use. So that's one thing we can get into, is just using that UI to tweak the parameters and to figure out what they do. But the special thing that just happened, thanks to contributions from several folks in chat, Mako MK was the one who actually found the key, but several folks have been working on trying to figure out how the encryption in the firmware images works, and we just got to the point where we can actually decrypt the update images and take a look at the firmware plaintext so that we can actually start to reverse engineer what the firmware does, enough to maybe find additional commands that might be useful. Maybe we can even find a way to just reset the parameters in such a way that it does a self-calibration. Maybe we can use that to get to the bottom of parameters that we can't figure out via other means. Maybe we'll have a better time understanding, extra features in the serial protocol this way. So that could be super interesting. And right now, that's pretty much just started happening in the Gitter chat room between streams. So this seems like a good time to continue that work and maybe poke at it in IDA a little bit and look for interesting stuff in the binaries. Just checking up, or catching up on the chat a little bit. Oh, sorry about that. Apparently, yeah, I forget that when I'm not wearing the headset, if I'm over there petting Tuco, then I can't really do audio introductions especially well. So, yeah, anyway, I think I'm not going to worry too much about having that audio, and I think I'll just try to talk through this as it's going. But sorry you had to sit through something that you probably couldn't hear. Yeah, Tuco's a great cat. I need to make a video about just how awesome Tuco is. And to answer Ken's question in chat, so the question was, did I get it working with the other gimbal? So I think the question is, I'm not sure what you mean by get it working. I mean, I turned up the, sorry, I turned on the other gimbal and it operates, and I was able to suck parameters out of it. I haven't really done a lot else with that gimbal because I don't want to, I don't want to brick it also. So I've been trying to reserve it for only tests that I know are really safe at this point. But yeah, it seems like that other gimbal's working as we would expect it to. Looks like Tuco's a little out of focus. Oh, also in a bit of news between streams, the Tuco Flyer Twitch channel is currently down. They actually canned it for 24 hours for a terms of service violation. Apparently they don't allow cat cams. But this was a thing on the IRL community for Twitch, so I think I'm going to try it again without any community tag. But I might wait until it actually has some amount of interactivity, since it seems like Twitch might just ban me again if I have a stream up there that is not strictly interactive. So that's the status of that. It seemed like a successful technical test, though. I had my stream going here for a while without any significant problems, so I think whenever I do have the robot ready to go, then the streaming infrastructure will be ready to handle it. I guess Ken has a lav mic suggestion. Yeah, I mean, I don't know about. I think my problem at the moment is more. So I don't know about lavs versus headsets, but the problem with having a mic that I wear at all has been mostly just getting the signal between me and the audio equipment. I have a wireless system that is not especially great. I could get a much more expensive wireless system that might work better, but I have a wire which works fine. It's just not super comfortable, so usually I just have the desk boom camera. Michaela's asking, So just so I get this right, all of this effort is going into a camera that can track the cat, right? Man, that's a lot of work to put into a cat cam. Yeah. I mean, what else are you going to do with all this technology? Yeah, I mean, but I think Tuco's a pretty great cat, though, and this will be a pretty nice project. Mikey asks, does Tuco randomly latch on when you pat him sometimes? My crazy girl likes to do that. I don't know if I'd say it's random. Tuco definitely gets into a really playful mood where he'll want to like bite and scratch and claw, which I can see if you're not expecting that would be annoying, but he only seems to do that. Like, it's one of those things that turns into a positive feedback loop when it's something that wants to play with him also, or like something that's trying to like fight back or run away or something. So I'll play back with him, and I'll get a few scratches on my hand, and we'll both enjoy the experience. Yeah, Tuco's pretty great. Oh, and this keyboard apparently was off again. That's better. There's still a big question, I think, in terms of what kinds of commands will be most useful for interacting with the camera. I think that's going to depend a lot on how much autonomy the control system has. All right, let's have the cat share the screen for a little while. We can use this one. I guess I'm also just surprised at all the, or like, I'm not surprised, but unamused. How about that? I'm unamused at the comments that are about just kind of being surprised at how much work goes into something, because that's like one of the high order bits for me. Like, I really like projects where you just put a lot of work into the details of something. And so, I don't know, I think a lot of people, like, that's the thing that turns them off, is seeing how deep it goes. But that's one thing I look for, is I want projects where there's a reason to go that deep into something. That's the part that I enjoy. I just want there to be something interesting on the other side of the tunnel. Okay, so this is the Raspberry Pi connected to the Tuco Flyer. Well, which currently is the gimbal. The Raspberry Pi is also going to be monitoring some other sensors, like probably a second LiDAR sensor, quite possibly a depth camera. But right now I'm just using this to run the Python code that speaks to the gimbal over the serial port. And the serial port shares wires with the pitch and yaw controls that usually come from the RC aircraft receiver. But when the gimbal powers up, if you respond to a packet that sends out in some amount of time, then it'll stay in a mode where it's waiting for serial port communications. That does mean that I'm probably going to have the Raspberry Pi control the power on for the gimbal and camera, so that I can be sure to power on the, at least the gimbal microcontrollers only after I have my serial port responding. So I'll need to add a load switch there for that. And so right now on the Raspberry Pi we have, well, this Flyer Logic repo is where we had our kind of camera steering tool with the Xbox joystick, which we haven't used for a while. And FY Gimbal, wow, why is my keyboard so laggy? Don't know if this is a network issue or a USB issue at this point. I think I've got some kind of ground loop problem on this side of the shop that I need to resolve. That's affecting the USB hub and the HDMI over here. Okay, so then the next stop. I've been keeping the work so far on understanding these gimbals in this FY Gimbal repository. So the work on the serial protocol here comes mostly from trying to generalize the packets that we've been seeing going between the gimbal and the parameter setting software that comes with it, which is super limited. All it really lets you do is change how fast it follows the heading of whatever's holding it. But by looking at the commands it uses for that and trying to generalize that, that led to this level of understanding of the protocol. So there's this FY-proto module that just has command decoding and a data structure for the packets. Then there's this FY serial module. This one builds on FY-proto to actually give you an interface over PySerial to speak to one of these gimbals. Oh, this looks like a network problem. Oh, geez. And now the streaming machine wants to restart to install updates. Okay, so then this is actually using threads to handle responding to, for example, that startup command in the background. So it's designed for kind of a blocking, REPL-friendly interface. So you can just instantiate one of these gimbal ports on the Python REPL and send stuff to it. And so I made this mostly with Jupyter notebooks in mind. So let's go to Jupyter and get an example of what I've been doing with that. So Jupyter is just it was originally known as IPython notebooks, but now you can use it with languages other than Python, so it has a more generic name, I guess. If I run Jupyter notebooks on this Raspberry, and I'll set the IP it's listening on to something that isn't localhost. Actually, let's just do this by domain. All right, so this is it starting up. And part of the reason I wanted to try using this is it seemed like a good way to just mash up the Python REPL with something that I can do, remote over the network. So I can have the Raspberry Pi on the flyer, connect directly with the hardware, running whatever Python code I want, and then dynamically inspect it from the ground just using a regular web browser, which seemed pretty compelling. That's the dream. So if you open this up, you'll actually get a little file browser that just shows you the same file tree that you started the Jupyter Notebook app in. If I open this Gimbal param space notebook, so this actually has just boxes full of Python code that run, and then it shows you the results. And additionally, using IPython widgets, this creates little bits of HTML that can interact dynamically with the server running Python code. So let's get this started. So the kernel's running. All of this stuff that you're seeing is just cached results from last time. I have to rerun stuff after loading it. So I'm going to run the first block. My monitor just went blank. Tuco, did you do that, or is it the EMI? Oh, Tuco. Oh. This would be easier if I could see the screen. I hear you, Tuco. Did you do this on purpose? Is this a cat problem or a grounding problem? Well. Okay. So that timed out because it was waiting for me and I didn't do the thing. Let's run that again. It should say... Oh, I might have to restart this because the serial port might be stuck open right now. If I restart this and then run this, then it should tell me to power on the gimbal, in which case I will power on the gimbal. So I think it's still waiting. There we go. And it timed out. Oh, gotcha. I think I'm just not getting the message I expected because I specifically set verbose to false. Let's just try that again, and I'm going to plug in the gimbal and hope it's listening. I think there's a bug in this. Live code debugging. Oh, yeah, I think I set this to check the verbose flag without thinking, and that class doesn't have a verbosity flag, and I don't care. I'm just going to let it print that. I don't expect to see CRC mismatches normally. Okay, let's try that again. So I'm expecting to see a message telling me to power on the gimbal, but I think with verbose set to false, I won't get that. Let's try this. Oh, that was it timing out. Okay, let's run this again without the timeout. That's the error that means that I have a duplicate port. Okay, I think this is working. I just need to do this in the right order now. Let's add a print here. Add myself a little note telling me when to power on the gimbal. Yay, that works. So, now we have a connection. One thing that I changed recently is that this will actually, if you run it again after already having the gimbal powered up, it won't make you re-turn on the gimbal, which makes the command line tools much nicer to use. Well, we'll see some of that soon. So this is running. Now here's an example. We can give ourselves a motor enable checkbox. So if I hit that, now the gimbal's alive and slightly wobbling. If I quiet it down, then it'll stay quiet, kind of. And I can turn it on and off. And likewise, I can run this and make some parameter editors. So the way this works, it populates the initial value once. Then if I click one of these toggles, then it'll start updating this dynamically. So if I hit this, then you'll see it refreshing this as fast as it can. Which it's kind of hard to see what it's doing just from this small amount of data. If I turn this on, if I turn both of these on, you should see it updated both of these. You can see it get kind of like little bubbles in the pipeline sometimes. I think that's where there's a timeout and then it's waiting for that. You know, it's like waiting like a half a second to get a response from one packet before getting a chance to retry. And then I have a little bit of a cheat sheet for what some of these parameters are. So 4 is the angular velocity from the gyro, which is why we weren't seeing it do much, but it was hovering around 0. 2C is the angles from the magnetic sensor. 8 is actually the current heading, which I think is actually a good example of a parameter that you can both read and write sensibly. So if you're just reading this, then like I think there are some things that might cause this to drift, and I think you might see this change if you were applying PWM inputs. If you had a way of reading these back also. But you can also just set these. So little hard to tell when it's laggy and when I'm controlling it incorrectly. But yeah, it like generally works, but there are some performance bottlenecks here. So there might be ways to optimize this, but this started me down a different path of just trying to do something simpler that was easier to make fast. So let's stop this. So we have some simpler tools. Let's kill this completely. He looks very nervous having his parameters set like that. Yeah, I mean, it definitely has some gain is set wrong, so it's very jittery. So there are a few little standalone tools. This controller thing is going to, so I'm pretty sure that the command that you use to send actual control inputs into it has a watchdog timer. So I've been experimenting with sending that command repeatedly. So far, haven't been able to do much other than cause the gimbal to twitch every once in a while. Param dump will just splat out all the current parameters in a big Python-friendly list. So, and you notice it didn't make me reboot the gimbal, so it'll actually work with, I guess it's hanging on exit for some reason. Maybe I forgot to daemonize a thread somewhere. Oh, or it was just a network pickup. Anyway, that's that program. Then we had a little bit of time with this one before, param diff. So this one just goes through and don't have the perfect layout for that. All right. So this one just scans the entire parameter space, and anytime something changes, if the parameter has never changed, then it shows up as normal plain text. But if the parameter has changed at all while this program has been scanning, then you'll see it in the bold green text. So this has been a pretty decent way so far of just examining what the parameter space looks like overall. Hey, Tuco. Yeah, I made a couple of changes since we saw this before. The green is new, and I made it go top to bottom first instead of left to right, because reading the columns is much easier. Hey, Tuco. So, one thing that we can try, which is a little bit new, is we could actually try running this program with the motors running, since this stuff no longer requires the gimbal to reboot. So I also have this set motors program. If you run it without any inputs, then it turns the motors off. If you run it with -- on, then the gimbal springs to life. And then we can do param diff. And this is actually showing fewer green lines, I think, because I think we aren't getting some of the really early parameters that change just as soon as the gimbal powers on. So I think these are the ones that I want to have listed as dynamic parameters in my list so far. Hey, Tuco, you sure are chirpy right now. It's interesting that the dynamic parameters seem to be mostly on the top half of this, you know, like in every other 8. I wonder if that was intentional. So I've been trying to label these as to which ones are dynamic and which ones are static. Try to get all this on the screen at once. Let's just compare this. So we have 2, 3, 4. I'm going to label these init since they only seem to change at initialization time. So then 4, 5, 6. So 5 is definitely dynamic here. Instead of dynamic, I'm going to put RW for read-write. I think that's the thing that makes the most sense there. 9 is dynamic. Then the next one is 28. And 2C, we've already got those. And then these over here starting at 47. That's good. So I'm missing a few from my other list. 4A, 4C, 6F, and 70. I think 6F and 70 were both related to motor power. These seem to be inverse of each other when I was looking at them in the graph. It seems to be settled down, like it isn't vibrating anymore. The current consumption settles down a little bit when it stops vibrating too. So that's kind of the flow so far. Is I have this program which is slow, but it scans the entire parameter space, and I'm using this to kind of categorize which ones are interesting to look at in real time. Then let's kill this and turn the motors off. Okay. So that gives me this list. Then the thing that I ended up doing as a replacement for the kind of slow IPython notebook here was I just made a raw WebSocket server and made a simple UI in HTML. So I've got this little param server here. The code behind this is kind of terrible because it's like partially asynchronous and partially synchronous. And I'm sure there are ways to get this to wedge, but it was a quick hot glue job for the moment. So this is actually a nice like asynchronous coroutine that runs per WebSocket client, but then it processes commands and just does like blocking get and set commands via the Gimbal port interface up here. And this is the whole server on one page, so kind of gross, but really simple. This lets you get and set parameters and turn on and off the motors, and that's all. It doesn't let you send arbitrary stuff, but it lets you update commands or update parameters. And this just operates on strings sent over WebSockets. It receives lines of text. Each line is a command, and the lines are based on tokens, separated by spaces. Then the UI is all just here in one file. I'm using one JavaScript library. It's a pretty neat little library called Smoothie Charts. If you search for smoothie.js. This is kind of uncanny how similar this is to stuff that I've written in the past in other languages and other UI toolkits. Oops, I just wanted to show the examples. So yeah, it's designed to do stuff like this in JavaScript pretty easily. So I'm importing that. Then I have a WebSocket to talk to the actual TucoFlyer server. And then I'm just I'm mostly adding things based on looking for looking for specific elements with a specific class in the document. So every time there's a canvas with this param class, I look for data that indicates what parameter it is, and then I set up a chart. And if there's an output with the param, then I monitor an output. And likewise, if there's an input, then when that input changes, then I send that to the server. And there's like a slightly aberrant case here for the motors, since checkboxes in HTML are weird. A little bit of CSS. And then this is actually how I'm defining basically the parameter space documentation for now, is I can just edit this HTML to kind of give myself a little dashboard, including some notes about what's what. So if I run this, I can run param server, connects to the gimbal, and gives me a little WebSocket server. And then this file I can just open up in a local browser. And this works because I have the address hard-coded in there on my network, which you could change for your own network if you're trying to reproduce this. There we go. It took it a sec to actually get data, but so now all of these should be updating in real time as fast as they can. This seems a little bit sluggish compared to what I'm used to. I wonder if my Raspberry Pi is having some network congestion. Oh, that looks... Anyway, let's try turning this on. Yeah, this is pretty sluggish. I wonder if I've got some network congestion going on. I'm expecting it to update way faster than this. I wonder if I need to not have this spewing output all over the place. Oh, Ken was asking what the current consumption is when it's settled. That's a good question. Right now I'm measuring the current... Oh, I started wobbling again. Right now I'm measuring the current of the gimbal and the camera and the LiDAR together. But I think with the motors off, it reads about 300 milliamps. And with the motor settled down to about as idle as they're going to get during normal operation, it's about 460 milliamps. So yeah, like 150 milliamps probably going directly into the motors right there. This is really sluggish. I don't know whether the problem is the Mac or the Raspberry. I assume it's something on this Mac because I've been mostly doing this development from a different computer but with the same Raspberry. Oh, is there something going on locally? Chrome helper. Is that just rendering this thing? I wonder if it's a DNS problem. Really shouldn't be, because I'm using a single connection and keeping it open. I can feel the lag on this SSH session. I think there's... What else do I have that I can use for comparison? Can I just give it a really quick ping? Oh, nope, 86. Huh. Well, that could be a bunch of things. See if I can SSH to... Well, I'm on the Raspberry. Can I ping something else on the network easily? Yeah, man, I think this Mac is having issues. Maybe we can switch to a different computer while this one reboots. That is touchy. I wonder if it's something with the network cabling on that machine. Anyway, let's see if we can dodge this problem for the moment. Do this monitor wiring. Okay, well, I'm on the flyer. The SSH session feels better already. Well, maybe this explains some of my problems with the Jupyter notebook. I don't think it would still be quite performant even if I wasn't having this network problem, but... Oh, this has been drifting already. Whew. Maybe let's turn the motors off first. Okay, motors off for the moment. Can I make this any more legible? Whew. That's better. Okay, are we in screen? I think we're already in screen, cool. Okay, maybe I'm tempted to go back to IPython just to see how much better it's going to be on a different computer, but let's just stick with the program and try the HTML UI for the moment. key on this computer. We can just download the file we need. Alternatively, maybe the Mac is probably done booting by now. Do we have any better networking now? I really don't know why rebooting would have fixed the networking, but maybe that's what happened. Okay. Well, let's try just picking this back up right here. Oh! Did I forget to check in that file? I think it's missing the smoothie charts JavaScript file. Yeah, let's fix that. Ah, there was a... Why is there a git ignore for JavaScript? Oh, there's a git ignore for lib. Don't do that. Okay, that's better. Well, that looks to be running. Any better? That seems better. There's a lot of lag on this, though. I think that might be something I'm doing wrong in the JavaScript side. Like, I know that there's going to be a bit of a delay the way this is configured because it's plotting stuff off the edge of the chart, and so maybe I need to change that. Ah, that's the delay. I think I've got a delay in there that's smaller than what I'm seeing. Okay, let's keep to only one repository here. Yeah, that seems fine. So I'm just going to avoid making a mess by only using the copy of this on the Raspberry Pi for the moment. Okay, so I don't want smoothie charts to have any inherent delay. And for timing, like it's using the browser's timestamps. I'm not getting timestamps from the WebSocket server. And it's just timestamping values as soon as they arrive on the WebSocket here, which should be fine. Okay, so I need to run param server and reload this page. Maybe I need to be not saturating the console with all that stuff. I don't know if that'll help. Maybe it doesn't know how big these charts are. It feels like there's an implicit delay here that I'm not controlling. For example, like 2C up here should be just joint angles. So like if I turn this, you can see that it responded with a new range pretty quickly, but it's like the data is way off of one end of that. So I wonder if maybe Smoothie Charts doesn't know how big these canvas elements are supposed to be or something like that. I think during an earlier version of this, I had the width and height set on each individual canvas instead of in the CSS. I wonder if that made a difference. Ah, maybe I guessed right. Yeah, I think Smoothie Charts did not have an accurate idea of how big its own widget was. Because now you can always see the new data, and you see a little gap where there isn't data yet. I think that's the mode I want to be using this in. Oh, maybe a 3-column layout. Well, so anyway, I'm getting caught up in how many steps there are at this point. So I want to go reconcile this with my latest list of which parameters are dynamic. But you should already be able to see, like, if I move this, you can see this responding. These are joint angles. A lot of these aren't labeled yet. And these at the bottom seem to just be kind of noisy when the motors aren't running. Oh, here's gyro angles. But let's turn the motors on. Okay, so it's pointing way over there. You can see the oscillations pretty clearly. So now I think 6F and 70, if you look, they're kind of complementary to each other. I don't know if those deviations from being truly complementary are just sampling errors, but I think those are related to the motor power. See how, like, right there, I was just fighting against the motor. Those two seem to be slightly different. I'm just not quite sure how yet. And I think, so also, I don't know why it's pointing way over there. I can use this target control to center it, but like, this is supposed to default to 0. I think. Yeah, I'm having to set that to like negative 15,000 to actually center it. And this seems to let me control yaw. So I think this control is being, or this particular parameter 8 is being read and written by some kind of algorithm dynamically. And so we can change yaw, and then it continues to drift a little bit from that baseline. We can change, well, we actually can't change roll at all. Roll just reads back as 0 no matter what. You can see on the next poll, this number gets reset back to 0. But yaw, if I change that, you can see the gimbal kind of ticks a little bit if you look closely. And so I think what it's doing is every time I set it, it's actually setting, but then it's decaying back to 0. Because I think there's like a pitch leveling algorithm that's turned on, which I would need to retarget or bypass. So I think what I'm seeing is there are several different control loops that are all coupled together. Like, there's probably going to be like a heading following loop, and there's probably going to be a per axis PID loop, and there's probably going to be some other control loop that is not per axis. And part of the job here is to try to figure out what parameters here are interesting. There's a lot of different ways I could focus on that. Well, first of all, it'd be nice to just modify this so that I have control over all the parameters that seem to be interesting to control, and that I have graphs of everything that's dynamic, which is just editing the HTML sum. You can watch this stay kind of stable until the oscillations build up again. There's a little drift in these motor control signals. I wonder what that's about. So yeah, there's a lot I could do with these to try to figure out what's next. Maybe before we dive too deep into that, it might be worth just taking a look at the firmware binaries also, since that's another exciting thing that we just got access to. Oh, interesting. See how these two are out of phase? I think that's actually like a beat frequency between the wobbling and the sampling frequency that we're seeing. The wobble is much faster than we're actually sampling at. You can watch most of those stop when I hit turn off enable motors. And then here's just a lot of these moving around as I point the gimbal. Oh, that's interesting. These sine waves here, I think these might be raw outputs from some of the encoders. I've got like several sine waves per rotation. As far as I can tell, 2C is the most processed output from the magnetic encoders. These seem to be angles between 0 and 4095. You can see the rollover point right there was 4095 to 0. That was the pitch experiencing rollover, like right in the middle of its useful range. Ken asks, what are the min-max of the angle position values when you're setting them? You mean parameter 8 down here? Just to be clear, I don't think these are actually in angle units. I think this is something like a deviation from the center position. But these are all plus and minus 32K, as far as I can tell. I mean, I can only really test the yaw, but the yaw seems to be plus or minus 32K. You can see the pitch doesn't even... Oh, see that? I was going to say that you can see the pitch doesn't even seem to allow to deviate from 0 even when the motors are off. But it looks like there's something actively setting it to 0 because I just got that blip where it was momentarily non-zero as I was changing it. And then it looks like the pitch control loop is off when the motors are off because this is allowed. I can set both the yaw and pitch to anything I want. I tried to do some tests to isolate the magnetic sensors and the gyros by taping the axes to the same angle and moving things around. I got a little bit of this info from there, but I think mostly to get further on here, I'd need to take kind of a methodical journey through each of the parameters and trying to see what they do. But just to make this gimbal more usable, the thing that's most, I don't know, that I'm most interested in really is trying to figure out how to change the gains, and also to just figure out why the yaw gain would be so far off anyway. One thing I was looking for would be parameters that were different for each axis, and well, I mean, so there aren't very many at all that are different from each axis, but ideally what I'd want to find in looking for like a calibrated gain parameter would be something that is not a round number in binary, so not something they just typed in, but something that they actually ran an experiment to calibrate. It could be some of these. These are kind of small to be gains, like they look more like offsets, but maybe. These are the same for each axis, so I don't know about that. These could be gains. And stuff like this, like I think these are likely gains or offsets that are not calibrated per device, but were just kind of typed in somewhere. So anyway, I think we'll come back to here in a sec. Mako MK says, I wonder if the wraparound is an artifact of not having the correct gimbal-specific offsets, or if it's meant to be there. Yeah, that's a good question. I didn't get any sense that that was a problem. Like, from my experiment so far, I don't see like a giant discontinuity in the pitch axis, so I think that's working as intended. I'm just checking what Sodium is saying. 64 and 4D as candidates. Yeah, I agree with 64. That's the one that I think I might try next. Yeah, maybe we'll just try that before moving on. Yeah, and 4C and 4D might be nice to take a look at. Well, so 4D is that thing that we thought was the stored center location. Yeah, sorry, 4D is what I'm interested in here. 4C is unrelated. Yeah, let's try that. So first, let's just make sure we have all the dynamic parameters that we care about before getting too lost in here. And let's not waste time on polling stuff that only changes at init. So dynamic, 4, 5, 6, 7, and 9. I'm just going to keep these in order, even though 8 is kind of weird. Four, 5, 6, 7, 8. 9, 28, 2C. This in 4, 7. 4, 7, 4, 8, A, C. I can remove 66 since that only seems to be initialization related. 6F and 70. Could be interesting to play with 6, 7 also, and because this is a parameter that just gets set to 1, but I'm suspicious that maybe this is some kind of mode or like a per axis mode. This could be useful. Yeah, 4D and 6, 4. This is really repetitive. This part could definitely use another layer of abstraction. These are all just saying slightly different things because there are separate HTML widgets for all the different inputs and outputs. We might not need the graph, but I'm just going to keep this for the moment so we can watch how it responds. Maybe a third column would be handy. Okay, so here's the new stuff all over there. Let's try turning on the motors carefully. It's still aiming way that way. Oh. If I actually set the heading to 0, then it's close to centered now. Interesting. Okay, so this is 4D is the one that we had been assuming was the center location. I don't know that it actually is, but these also are probably not the full 16 bits. Oh, I can change this one. Can't tell if it's having an effect. Whoa. Setting it over a particular value caused the yaw to go sharply in one direction, even though that was not the yaw axis I was changing. Whoa. Now it's going unstable and drawing like 90 or 0.9 amps. I'm gonna turn off the motors. Wow, that was interesting. So I think what just happened is I tried changing the first axis, which is usually yaw, and didn't notice anything happening. Then I tried changing the second axis, and it seemed like there was a point at which moving past that point caused the yaw to just flip directions. And then changing the third parameter, which would usually be pitch, moving it past a certain point just caused it to go into like circular jello mode. Oh yeah, sorry, that was off screen. Let me try reproducing this anyway, because I need to try this again. I also think these are probably way, like I think the range on these sliders is probably way too big. I kind of want to give this thing fresh parameters right now. Let's just splat the default parameters. There's probably a version of this that doesn't save to the flash. RAM server, reload. Okay, so here's what we've got. The negative 400 is just something I made up that seemed to be better than what was there before. I don't know what that actually is signifying at the moment. Then the other two, I think, are copied from the dump from the good gimbal. Well, let's try poking with these again. So enable motors. That's pretty settled. Nope, still a little wobbly. Okay. These are the two motor power related outputs that I was mentioning. All right, now I'm not touching it. And then the oscillation starts. So whoa. That changed direction when I went negative. And it stopped wobbling when I changed that to 2. And the current consumption's pretty okay. It's like half an amp right now, including the camera and the LiDAR. It's a little bit jello-y, but not that much actually. Huh. This seems like it's alright. Well, I mean, clearly I don't understand what I just did, but it's nice to know that it seems possible to improve the situation. I mean, yeah, that might have been like one of the gain parameters right there. Let's see if I can command this while we're experimenting. So heading... This is no smoothing. But despite the no smoothing, it's kind of the thing I want. Oh, good question from Sodium. Is it still drifting? Yeah, I guess I'd have to let it run for a little while and see. Oh, it's still a little wobbly near the center. But yeah, is it drifting? We could check the video output from this. It's also, the roll is not centered. The roll axis is actually off quite a lot. And I can't change roll through this parameter currently. And this one still only has a temporary effect. Okay, maybe we can very slowly change some of these parameters, I think, with the keyboard. So what if this is 0? It's not like 0 gain entirely. What about this one? Whoa. Oh, geez. Yeah, I need much finer control over these parameters. That was much bigger change than I wanted to make. Let's at least label these a little. Give those some pretty simple names. I'm going to assume that we probably want these. I think these were positive. So I might want a little bit of negative range, but not much. Let's see, 4D and 64. I think originally this was positive. Let's check the diff. Or actually, did I just save that in here? Fresh params. Yeah, those were all positive and close to the same value. So I'm going to try just giving myself a slider between like 0 and 5,000 or something like that. I'm choosing something somewhat larger than 4096, which I think might be the actual limit. But these don't have to be really accurate. I just want to get closer to the region that's probably interesting. Why are these so little? Oh, these sliders aren't getting set to the current values. That seems a problem. I guess I'll just set those manually. Yeah, let's just set those to like 2900. Okay, I'm not going to bother implementing the code to pull in the actual defaults right now, but I'm setting them in HTML to be close. So, enable motors. It's a little wobbly. Okay. This feels like an offset, like there's a point around which it just wants to pull really hard to one side or the other. Oh, maybe it is a gain. Maybe it just... Whoa. Huh. It feels like it's accelerating in that direction, like that isn't just gravity. Like turning this down to a point damps out the oscillation and just like that just feels like the axis has been gained down a lot. Like it's really limp at responding to the yaw. But then when I went lower than that, see, like now it's actually moving the wrong direction. So maybe this is encoded somehow with like a sign bit in there or an offset, or above 0. I mean, it would make sense maybe for them to encode a couple of things in these parameters if they're trying to keep the number of like calibrated data units that they're sending to each gimbal relatively compact. So it looks like what I've just done right now is turned the gain on the yaw axis way down. And it feels like it still has some cogging going on, like there's some locations that like there's more than one location that it might settle into. Anyway, let's try the other axes and see if they behave similarly. This one is what I would expect to be the roll axis. Yep. Similar behavior. I went down past some point and then the roll axis just torqued in completely the wrong direction. But then, now at like 2100, now it just feels kind of limp, like it's not really... I wonder if this is hysteresis. Because it doesn't feel like just a gain parameter. It feels like something more complicated, or maybe at least something like more than one value combined together, maybe. Just turning it up slowly, and now the roll is actually coming into, like now the roll is actually holding all right. Also, the points that I'm getting different behaviors at, they might be just like rollovers happening elsewhere in the algorithm. Like they might not be intentional. It looks like that point is around, not 2048, but like 2100 or so. 2100 seems to be a pretty low gain. I'm just stepping it by individual increments. Oh, interesting. Yeah. This is now locking into the wrong positions. I'm at like 2090, and it's like it's off by an entire motor phase or something. And now around 2100, it's not a sharp cutoff though. It just goes from holding kind of the wrong position. It's still drawing a good bit of current. It's like 800 milliamps total right now. Yeah, this maybe isn't a gain. Maybe this is like some kind of phase offset for the motors. Because it feels like maybe I'm having the effect of decreasing the gain, but maybe what I'm doing is decreasing the motor efficiency. And around here, the current settled down to like 650 milliamps total. And it actually feels like the motor, that axis is stronger. So I don't think I was decreasing the gain. I think I was decreasing the motor efficiency, at least from this experiment. Oh, I'm a little behind on chat. Yeah, for checking for drift, I think the easiest thing to do is just to plug the camera in and like watch the picture move, because it's actually pretty easy to see the small changes on the image. And then I'm trying to parse what Mikey is saying about the parameters per gain direction. So the way that these parameters are structured, so when I have these tuples of 3 values, those are actually coming from each of the 3 different microcontrollers. So it would be really unusual to see something that's like yaw axis specific that only shows up on like the pitch microcontroller or something. Like that would indicate that that functionality is being delegated to a different microcontroller probably. So it might happen, it's just would be weird. Let's try the video output. Butt cam. All right. Here's the gimbal. Hello, gimbal. There's a little bit of the wobbling coming back. My yaw axis is still pretty limp. But you can see it kind of settling into... See, I bet this parameter is motor related. I bet this is a calibration for the motor, the offset between the motor phases and the magnetic encoder or something like that. Yeah, maybe the thing that's calibrated at factory isn't the gain at all. Maybe the thing that's calibrated is mechanical parameters of the sensors. Let me try loading my default parameters in again, and then we'll check quickly for gain, because right now my parameters are a little messed up. So I'm setting defaults. Oh, I've never set defaults while the motors are on before. That's probably not a good idea, but that's what I just did. And it's still having trouble settling down in the yaw axis. Whew. The motors are kind of warm. I think that last experiment was probably running the motors kind of harder than they usually run. Yeah, let's switch cameras. So now the whole thing's back to like 600 milliamps, which is more normal. So yeah, my stab here is that 64 is actually a motor phase offset calibration. That's probably what I'm going to call it. I'm going to turn off the motor for now because I can't quiet this down. All right. And back to our regularly scheduled Tuco cam. So I'm also, I bet we're going to see these parameters grouped together. Like, you think this is all the motor-related stuff, maybe, and this seemed to be gyro-related stuff up here. I would expect to see some kind of grouping like that. I'm going to call that motor phase offset calibration with a question mark. Now, could we figure out, I don't think we've really tried 4D since narrowing the range of adjustment. Maybe we could play with that a little bit too. Okay, so there's motor phase offset calibration. I assume that the way to calibrate this is going to be based on motor efficiency or like, maximum motor torque rather than actually trying to calibrate it like a gain loop. Let's take another shot at what 4D might be doing. So motor's on, and we're wobbling again. So let's try to see if we can resolve the wobble without just making the yaw motor super inefficient. That's interesting. As I change 4D, 4C appears responding. So I wonder if 4D is a target and 4C is an error. Oh, look at that. 4C seems to be 4D. Yeah, I bet 4C is the error and 4D is the target. But I wonder why it doesn't seem to be updating. Oh. It just started, whoa, I don't know what I just did. Changing the next parameter, which would usually be roll, seemed to cause yaw to behave differently also. I wonder if there are just different behaviors for moving it back into range, and I'm... Oh, see, that discontinuity was actually causing it to try to move a different direction. But that seemed to be affecting yaw, even though that's not the yaw axis I'm controlling. Whoa. Interesting. That just affected the other axis up here. Well, these motors are kind of warm. I'm going to give them a rest. Maybe this is a good time to look at the firmware. Oh yeah, just catching up in chat, the known good gimbal values from the other gimbal, yeah, that's exactly what we've been starting with here. We've got dumps from the bad gimbal, we've got some... Well, actually, maybe we should take a look at the old dumps now that we know a little more about what the parameters mean. This is the dump I took of this gimbal when it was not working right before splatting its parameters from the working one. Oh, it'd be nice to have a tool to diff these a little nicer. Let's turn off that picture-in-picture to get some more room. we really need a better diff tool for this. I mean, ideally, maybe a spreadsheet would be awesome for this, or something along those lines. Oh yeah, Peter's mentioning that maybe that has something to do with the sensor axis instead of the gimbal axis. Yeah, I mean, maybe they're breaking up the work somehow in a different coordinate system. Okay, what format do I want this in? I think I just want each of these turn into like a column of a spreadsheet. I think we want something like this. I think that's what we want to start with. Trying to pick an appropriate level of automation for this task. I don't really want to write logic about these files that much because I'm not really going to keep other dumps like this. I just want to have these Python data structures. maybe I'll just start with that. Something that'll dump these out on the command line, or on standard out in a nice rectangle. What did I do wrong? Oh. Okay, that's more useful. So you can see the version number at the bottom, a bunch of unused stuff. These are the motor power levels, which are just going to be fluctuating a bunch. Oh, I wonder if this is where all the zeros went. I mean, I did try writing zeros to this gimbal before saving this. You know, this value for param 8 is pretty messed up. I wonder if that by itself... Oh! Actually, how is that even happening? Like, 8 is the target heading. I've never seen a non-zero value for 8 roll. This might indicate that in this parameter set, whatever is setting this to 0 is turned off. Yeah, these values seem like a problem. And 4C. Are magnetic sensor values. Yeah, I don't know if that's amazingly enlightening right now. Piotr's asking if I found where the mode is saved. I think that's dynamic. I think it... I don't know which... Yeah, I haven't had a chance to send it pulse width modulation input and get access to the parameter space at the same time, so I can't just send it like RC servo mode pulses, but yeah, so in that dump I think I had written stuff to zeros, and this, what we're seeing is the stuff that it set to non-zero value mostly. Anyway, maybe this is a good time to take a look at the firmware. So, here is the firmware. You can follow along by downloading this from their website. So yeah, they have a website, feiyutech.com, support. Then this particular one is the Mini 3D. There are probably a good amount of overlap between the firmwares and their different products. But this is the file we've been using. There are other versions available here too, but I've been mostly using this latest version, 1.15. So that's where you get this .bin. If you look at the .bin, it looks pretty encrypted. But several of us have been taking a look at this. Like, I mostly haven't been going super deep into this so far, since I was more interested in taking a look at the live behavior in the gimbal. And it seemed like it was going to be a ways before we could get actually any useful information on how to use these gimbals out of this firmware blob. But despite that, we kept making some progress. I did end up connecting a debugger to the gimbal through the serial wire debug, or the serial wire debug port. The flash readout protection was set up, so we couldn't just read out the decrypted firmware. But I made a RAM dump, and then based on this RAM dump, Mako MK, who's in chat right now, thanks so much. They were looking at the RAM dump for potential AES encryption keys and found a candidate that turned out to be right on. I think the method was just brute force decrypt using all of the, all the different values that we found in RAM. Just try everything and find something that's low entropy. So that's what we've got. The key itself was just hanging out in that RAM dump. So if we take a look at the RAM dump, that is in the GitHub repo for this project, in this RAM 2000, etc. This is just a live RAM dump that we got from attaching the debugger to the gimbal. We can't single step at this point since flash readout is disabled, but we can read RAM. So the first part of this is going to be stack. A lot of zeros and stuff, some signed numbers, more signed numbers, some more stuff. This could be uninitialized or maybe compressed or encrypted data. But the thing that actually, I think, ended up having the goodies, I think it was one of these structures here. Not that one. Yeah, I think it was this one. So, in fact, it's pretty easy. Like, I think that Mako MK originally did this with brute forcing, but if you look through this, you can even kind of notice which of these are likely crypto and which of them are just like normal detritus from running the firmware. There's some interesting bits. Like AA, or combinations of A's and 5s occur as magic numbers around here a bunch. Those are used in the serial protocol, so some of those might be related to like serial protocol buffers. Some of these might just be, side effects of other things that the firmware is doing. So this first part's going to be stack mostly. This section here is kind of interesting. Repeating patterns. Doesn't look like crypto, but looks like there's some kind of like byte tag format or something, or maybe just a bunch of short integers that are close together. bunch of zeros, more low entropy stuff. This looks like signed 32-bit numbers. More AA55 related stuff. You can see the diagonal stripe pattern through there, like there's a repeating data structure. And so this has more of the A55As. Also, if you search for the firmware version in hex, so this is 115. If you search for 73, you know, you'll get some spurious stuff because it's just a byte. But like these, I think this is a buffer containing those initial packets that contained the firmware version that get spewed out when it first boots. So I think this might be the serial transmit buffer. This looks like another copy of that same command, maybe related to the last command that was sent out. So we can already kind of start to map out interesting RAM locations that we might be able to control. And these don't seem to be related. One reason I was looking for 7.3 was to see if there would be a copy of the firmware block itself just hanging out in RAM. Because I still don't know whether the firmware, like these parameters that we've been editing, I don't know if that literally maps to a chunk of RAM, or if there's some code that ends up basically running a switch statement every time we get or set something out of here. So one thing I wanted to do to determine which of those it was to try to find something that could have been a default parameter block hanging out in RAM. Or, you know, we found a default parameter block in Flash, but, you know, in RAM, I would expect to find the current parameters if it wasn't something that was kind of synthesized together by code. But this does not look like the parameter block. This looks like some other 32-bit stuff. You can see 32-bit integers here, probably. Some other stuff like addresses that seem to be 32-bit aligned. That might be the version, but it might be something else. And this is probably uninitialized memory, but could be something else. So yeah, unless it was that chunk of memory that was sort of oddly shaped, it might be that they're storing each of the parameters in a 32-bit number in RAM and then just encoding it as 16-bit on the wire. It seems a little wasteful, but, you know, maybe they had extra RAM to spare. And those are definitely packet buffers. Yeah, so this chunk here I think is the best candidate for something that might be parameter related. But I don't think that's going to be a direct match. Like, I would expect to see, like, even if they were storing it in 32 bits, I would expect to see a bunch of values where the high bits were always either 0 or FFFF, and that's not the case. So my guess is that they're actually synthesizing that. Anyway, the block that we found that seemed to be crypto-related, just to get back to that, was, I think, not that one, but I think it's this one. So, and then I wasn't really involved directly in this, but I think MakoMK and Robert in chat were taking a look at this, and they noticed that the, oh, and also Michael Adoltsov was taking a look at the patterns of commonalities between the individual blocks. And so, yeah, it was definitely a team effort. And then I think what happened to really spark off the next bit of this discussion was MakoMK trying out kind of a brute force of just all the bytes in here to see which ones could be key material. And so that led us to the next bit here. So we've got this, an unpack script. So this is the value from RAM. Let's find where it actually happened. Yeah, DA. So this is the last 16 bytes of this chunk. So I think the way this is set up is this is there's like a length up here and a pointer, so this is the beginning of some data structure. And then this is actually the internal state of AES, so this is the key schedule after the key's been expanded. But I think it was in a bit of a weird format, which Robert and Mako MK took apart. It was like the endianness was kind of strange, and so yeah, I haven't looked into this directly, but from what I understand, based on their investigation, this is the key schedule, and then this is the actual key itself. And we already knew from some earlier poking around in this kind of the overall structure of these firmware files. So the first 8 bytes of this is actually a header. So you might notice right away that this looks a little bit less entropic, like this seems kind of random, whereas, oh, we have 3 repeated values. And so the header, this is actually probably a checksum. This also shows up in the Windows software as a CRC16 of some sort. Then this seems to be the size of a firmware image for each of the 3 microcontrollers on the 3 axes. And then everything else in here is organized in 1024 byte blocks. And so we found on an earlier stream, I think, that the empty areas of this thing all seem to be the same block repeated. And so that seemed to be an artifact of the encryption mode they're using. It looks like AES CBC mode. So what they're doing is it starts out with an initialization vector, and then you encrypt a sequence of 16-byte blocks where each one, the ciphertext feeds back into the next one. So the initialization vector matters for that first block, but then after that first block, if you're decrypting at least, the next 16 bytes, its effective initialization vector comes from the previous 16 bytes ciphertext. So because of that, what we can do next, I'm just going to go back in time a little bit before we had the initialization vector figured out. So just using the key that we found kind of hanging out in RAM, and let's just assume the initialization vector is all zeros. This little Python script is just going to open the firmware file that we found on the website, read the header, we're ignoring the CRC for now, and then for each of the 3 microcontrollers, for each of the axes, it's going to decrypt a single kilobyte block at a time. And so each of these blocks are decrypted separately, which is why for the empty regions in the firmware, you see a repeating pattern of 1 kilobyte, because it's just taking the same data and encrypting it and giving you the same result, which isn't the most secure way of doing this. You could use a different initialization vector for each block, but I've seen worse. So all we're doing here is decrypting each of those blocks using the key and initialization vector up here. So if we run this, so it looks like I don't have PyCrypto installed. Just doing this on the other computer. And I had this problem too. I think something changed where PyCrypto is now lowercase in the pip file, in like the wheel file that it downloaded, but it doesn't seem to actually work in that state. I think that's what I had to do to fix this before. Maybe that didn't do it. Or maybe this is a different package. driving beat is coming from the stream. Am I broadcasting audio unintentionally? I don't hear any audio broadcasting. Judas1911 in YouTube chat asks, do I build doomsday devices for fun, or is it my job? Do I have to choose? Oh, see, now I have... Yeah, so I do have PyCrypto installed. I think this has got to be some case confusion bug in pip. And then I do that again, and I think that'll fix it. Yeah, okay. Okay, so that worked. So just for some more context, this is the version of Unpack where we're using a key that we found in RAM. We're using an AES mode that we guessed based on the repeated blocks that we were seeing. And we're using an initialization vector that's all zeros for now. And we get these 3 files. We're just going to pick one of them arbitrarily to look at for now. So it's already looking a lot more plain texty than before. You've got some structure here, but it doesn't quite look right. And then the quickest thing to do is we're pretty sure that we have these blocks that are either 0 or FF. So because of the way AES CBC works, we're going to see each of the first 16 bytes of each of those 124 or 1024 byte blocks. This is going to be the initialization vector XORed with the plaintext, which in this case, I think the plaintext is 0. So in that case, this is just the initialization vector. And in fact, if you look at what we had in the file before, I just Control-Z'd my edit, and that's exactly what we have here. So if you run this, assuming the initialization vector is 0, and then find a 0 block, or find something with a known plaintext that you can XOR, then you can get a copy of the initialization vector. So with that, I can run this again. Now we're actually seeing some signs that this might be correct. So if this is the beginning of an image, this is looking like an interrupt vector table. We have a stack address, which is in RAM. We have something that might be an entry point in Flash. We have some other Flash addresses. And then we just have some numbers. Some signed numbers, apparently. There's a big lookup table, which seems to be like a signed 32-bit field of numbers of some sort. Then now we're getting into some stuff that might be code. And we'll know if the initialization vector was right if we go down to this field of zeros and it's actually all zeros. And it looks like that's right. We're not seeing leftovers from a partially decrypted first 16 bytes there. So that's our firmware image. And so because we have 3 microcontrollers, there's a separate firmware for each micro. This is a nice trick for just checking out the entropy. We can see that the middle micro is a little bit smaller, and there's some code that's specific to the first one and the last one. And I think this fits in with the theory that we've been operating under so far, which is that all the micros have some common code to deal with their motor, but then the first axis, which in this case is yaw or microcontroller 0, that one probably has some code to handle the RC servo style inputs. And then MCU2 has some code to handle the IMU and probably some global kind of all 3 axis kind of control loop features. So if we were picking one of these to reverse, it might depend on what our goal was. Like if we started out with MCU1, it would be simpler, and then we could just look for what's different on 0 and 2. If we were more interested in the IMU and figuring out all the parameters, MCU2 probably comes the closest to knowing about all the parameters. If we were interested in figuring out how the kind of frontline interface, that 115 baud serial and the pulse width modulation, all of that's going to be implemented in MCU0, so we would take a look at that. Might also be useful to just take a look at this in BinViz, since I thought that lookup table looked pretty cool. So MCU2 is the meatiest. Let's take a look at that one first. Oops. I am very zoomed. I don't know why I can't zoom out anymore. That's a little weird. I guess I just have to change the aspect ratio. Huh. Whoops, sorry, Gimbal. Oh, right, this is still gzipped. Ha ha ha. Why does it look compressed? That's better. Oh yeah, thanks for the hint. Ooh, this is much nicer. So you can see that stuff that I was thinking was a data table at the front is super low entropy. Yeah, this would probably look more interesting if we graphed these as 16-bit numbers, but I'm assuming this is some kind of math lookup table beyond the obvious interrupt vector stuff up here. I feel like it would probably make sense for this to have like a logarithm or a trig lookup table. There we go. Actually zoom out more. Yeah, these could definitely be trig tables, both of these. And this is also a lookup table. Then this seems to be code or something. Empty space. You know, if we were going to look at the parameters and the defaults, it would probably make sense to just look at the serial handling code in here and try to figure out how it's storing parameters and just generally find the implementation for the serial commands. This is the block at the end that we were thinking might be default parameters, right at 18,000. It has a 7.3 right where the version number should be. So I think it might just be time to load one of these into IDA. Since I'm inclined to maybe start with MCU 0, since that's the one we're directly talking to. It'd be nice to see its serial input handler, really. Oh, good question from Mark WHI. Now that you have the AES key and the raw firmware, can you repackage it and remove the flash protected bits on the MCU so you can single step? Quite possibly. The one gotcha about this is I think we don't have the bootloader yet, which we might not need, but running this without the bootloader might involve at least like making a little stub bootloader that calls this properly. So, and I'm getting a little bit ahead because Robert from the chat has already been trying to get the addresses to match up, and I think they've got a load address that works. But I think the next step is actually to look at how this might fit into flash memory and to see if we have a good entry point here. So if this was an interrupt vector table, then this would be the stack address, and this would be the reset vector. So I think so. What is this 1 doing here? Does that, maybe it would be worth checking out the memory map for the CPU, since this might be something I need to look up. I had just gone back to find the specific CPU model number, and I wrote it in chat right before the stream started. Yeah, this one, STM32F103. Is this going to be the full data sheet? Memory map. So yeah, flash memory is right there at 0800, but I thought we saw something at a different address here. Yeah, this is not flash, this is something else. So yeah, this might not be an IVT, this might be something else. We might also just find some data structures that have pointers. Oh yeah, just catching up on chat. So Piotr says the bootloader might be write protected, and the problem with reflashing the bootloader means you need a stub that has to load the payload. Okay, so you have to have a stub that you need to load to the payload, unlock the bootloader flash section, then reflash the bootloader. Yeah. Huh, are these floating point numbers? This still seems like we're in data table land. Well, I don't know. And that's just the end of it, right? Oh. I think maybe that was a decryption artifact, because MCU0 has addresses that look fine. Check that. Oh wait, no, that's not the most significant bit. Oh, maybe I'm just getting confused with XXD's endianness. I think the way that it separates these into 16-bit numbers, I keep assuming. But no, this is the high byte. So that is correct. Okay, yeah, I'm just confusing myself with the endianness. This is right, it just is later in Flash. That's the high byte. That's the next significant byte. So these are all still well within Flash. Never mind, false alarm. So if this was... So we would expect this to be the address of something that looks like a function in here if we subtract the offset this was loaded at. So it seems likely this is a multiple of flash block boundaries, which Peter's already been talking about as 2000 hex. Oh, and then Mako MK is already a little bit ahead, and they're getting some weird addresses for MCU2. What do we have in here that's pretty early? I see some of these at like 2.5. Here's 2.3, 2.1. Oh, here's some in the ones. I wonder if those are bootloader addresses. I mean, it's quite possible that if this is an interrupt vector table, that it might be directing some of these to the bootloader. It might be useful to just find, well, something. This might be a good starting point. This thing that's probably an entry point. So this is 0008, sorry, 0800 FFD2, or D2FF. So maybe something at B2FF or thereabouts. Let's just see what, and if this is a code address, it probably actually starts at 2FD. Since this is thumb code, it's going to have that lowest bit set. So maybe we'll just look for something at a 2FF or a 2FE that looks like thumb code. That's still deep in data table land. That's still data table. What is a... I mean, that's a candidate, 32F. I can't disassemble thumb off the top of my head, but maybe we have a tool that can. We're gonna have to give this some incantations to make it disassemble raw thumb code. Can't binary that. Maybe I'm forgetting how that works. Oh, dash lowercase b binary. I don't see a dash lowercase b, but sure. Okay, now it just needs an architecture. I don't know which machine that needs to be. I thought there was a command line option to just to list out what machines were compiled in. I don't know why I'm not seeing that. Oh, dash info. Those are formats, but not machines. Does it just want ARM? That's what I wanted. Okay, so disassemble all, force thumb, architecture ARM, and binary format. Great. So this is MCU0 on version 1.15. And I'm looking for candidates for load addresses. So this comes from up here. This is probably the entry point if this is an interrupt vector table. And I'm just assuming there's going to be some kind of offset in a multiple of flash pages and looking for something at this FD2 alignment that seems like maybe a function. 4FD maybe? Is that like a function? Oh man, 4FD2 is totally a function. So this could be our load offset, B000. Let's see if we can come up with a smaller load offset though. If we can find something closer to F, that means the load offset is smaller and the bootloader is smaller, which is more realistic. So it can't be any of these. Could it be 8FD2? Probably not. 7FD2? No. It could be 6FD2. Which would indicate an offset of 9,000 hex. That's still a pretty big bootloader. And I think the flash sectors are not divisible by that. I think B is more likely. Let's check out 5 just for completeness. That is not disassembling like code. Could be aligned wrong. I think maybe this is the bootloader size, but let's see how that jives with the flash protection block sizes. Oh, Mako MK is asking if I've got the bytes the right way around. Did I mess that up again? Oh, I did. 8D2F, yeah. I really am not used to these hex dumps. Maybe I want G1 for these hex dumps. That's better. Yeah, I don't like my brain when I see numbers that don't have a space between them. I assume that they're integers and not just a string of bytes. So this is much more sensible to me. So yeah, D2FE is what we're looking for. Maybe we can find a better offset now. I'm just decrementing this and seeing if we can find an exact match. Huh. That doesn't seem like it. But that's a weird little bit of code. I don't think this method is going to actually be super reliable, because this can really easily miscode since it starts disassembling from kind of arbitrary locations. Oh, maybe I should actually pay attention to chat. I know people have been yelling at me and I haven't been looking. Oh, nice, a DFU uploader. Aw. Well, I appreciate the kind words. I was checking at chat because I thought there was something like urgently distressing, but it's nice to see something positive. So, I mean, I'm feeling a little bit frustrated here because there are many different ways to proceed, and this doesn't feel like necessarily the best one. But, like, you can just load stuff into IDA or any other disassembler and start playing with it. At some point, very soon, I'll want to stick this in a more capable tool, which will probably just be IDA. I would like to learn more about Radare tool too, since it'd be nice to have an alternative to IDA that's not expensive. But I was hoping to use objdump here to just do some disassemblies before loading it in there, just to get the address set correctly, since I think it will, like, it's kind of annoying to, like, I don't know of a good way to, like, clean up a database if you end up loading stuff at the wrong address. I usually would end up starting over, or, like, I think you can fix it, but it's kind of a huge pain. So I'd prefer to have the load address correct before loading it into IDA. But it's also possible, like, I just load it into IDA and do this part in there because it's a little bit nicer than trying to objdump from the beginning and then hope you get the code that you want. So let's go ahead and do that. Let's switch this over to IDA and keep this stuff handy, but maybe do the rest of this in a slightly more powerful tool. See if I can drag and drop these into Windows. Yay, MCU zeroed up bin. Okay, binary file, ARM, and we want to tell it at least that this is a thumb-only processor, so ARM7M architecture will help with that. And hello? Now the UI isn't responding. Maybe I need to reboot this VM. Oh, I think it just came back like right before I rebooted it. Oh well. So much fun waiting for Windows to boot. Man, I feel like I'm terrible at byte orders. I think, I don't know, maybe there's gotta be some kind of like byte order prosthetic for people who are a little bit dyslexic. Alright, let's just open this up. ARM 7M. Great. ROM section. So I'm going to start this at the beginning of Flash right now, even though I'm pretty sure that's incorrect. Oops. Load address. Okay. Here's our beautiful hex dump. So we've already got some nice pointers there. So yeah, we know that this is not right, because otherwise this should be pointing to code. But D2FF minus some other number should maybe give us some code. So D2FE minus 2000 maybe? Can I not do math in here? Oh. Yeah, I can't do math in here. Oh well. B2FF. 9-2FF. Just does. Yeah, we saw this before. This was like in the middle of this no-op contraption. Which could be it, honestly. Like, maybe they start the entry point with a bunch of no-ops just for working around some hardware bug. This thing that was right before it seems to be an infinite loop. But this seems to be assuming this would not return if this is even a real function. You know, this might be something. This might be a weird way to get into the program, but it might be a thing. And that's 92FE. So that's what, two flash blocks. Yeah, I think that's 2 flash blocks. How big is our flash block again? One kilobyte pages. But actually I want the protection granularity, not the erase size. I think there's a bigger data sheet I need for this. STM32F103 Flash Programming Manual, is that what I want? Or is there just a big all-in-one manual? Maybe this is what I want. Reference for all the STM32. Memory architecture. Boot configuration. Embedded bootloader. That doesn't seem like what we'd be using right now. Flash pages, 1 kilobyte. This is the part of the chip that we care about. This is where the protection and the protection granularities are going to be. Flash module organization. Yeah, I don't know why the bootloader would be so big then. Because it seems like the bootloader, like if this is right, it means the bootloader's like 16K. Would they have a 16K bootloader? Is that realistic? I mean, I guess we could just try this. It'll, if we're wrong, we just end up with a useless IDA database. But why would they have a 16K bootloader? You know, I think this also matches what Robert was seeing earlier in chat. So I guess that's another point of corroboration. I'm surprised their bootloader's so big. So let's start a new IDA database. Same options here are going to be all thumb. So let's actually bother with the RAM and ROM segments maybe. I'm just going to make these kind of arbitrarily large. I'll make the RAM and the ROM a megabyte for now. And the input, that'll go 16K after the beginning of the flash. Let's see if that works. So there's the beginning of the file. This is looking right so far. These are all interrupt handlers that just go to infinite loop stubs. We'll assume that's the entry from the bootloader. More functions. A lot of unused entry points. This might be that data table we were seeing. I'm going to assume it's 32-bit values, but let's undefine this. If I find the thing that's after the data table and then come back here, then it'll be easy to set the size. That is still data table-y. Oh, wow. So we've already got a function that's right after the data table. So let's just define that and see how big it is. $1,026. Let's try rounding that down to 1024 and see what that looks like. This looks like a trig lookup table. Yeah, maybe that is actually 1026. Sometimes trig lookup tables are a little bit larger than a round number like that. So yeah, let's just set that to 1026 and assume that's the entire thing. Trig lookup table. Okay, I'm not going to assume it's trig yet, but it's probably trig. So a lot of these are probably boring. One of them is probably serial, and it's probably going to buffer stuff in a queue in RAM. And then something maybe in the main loop will handle the commands. What that is. Hardware access. Yeah, maybe, I mean, there are a lot of things to do. If I was going to go straight for serial, I could just look for the IRQ or the memory regions associated with serial on this chip. I wonder what we have here. This seems to be a different table. Yeah, this just seems to be a second lookup table. And this is using both of those lookup tables. What a coincidence. Oh, is this another table? Maybe that's our third table. Another data table, it looks like. I think this one's 16-bit. I don't know, this one might be something weirder. There's like a little buffer of stuff it's copying somewhere. This is kind of a pattern. A1, B1, C1, D1. Yeah, I wonder what this is. Maybe another lookup table is all. Does this make more sense as 16-bit numbers? $256 16-bit numbers. Another lookup table. Maybe. Maybe a multiplication table? Interesting. Just going through undefined data right now, and it's mostly stuff in between functions. This is all stuff that IDA hasn't already been able to figure out just based on following the chain of, references that I've already given it. So there's some stuff in between functions. There's some like little tiny data tables. This is all pretty unexciting. Another data table. These are all hardware register addresses, I think. This stuff doesn't decode as code. I think this is, like, we're jumping over it, and then I think we must be using the return address as data. Oh, we found a wait for interrupt function. These might be some wrappers around system-specific stuff that might not be used. It's like turning on and off interrupts and setting interrupt priorities. Ah, that's a no-op. That's a function. That's a function. I don't know if that's a function. Yeah, I don't know what that stuff is. That's probably also not a function. Oh, we're near the end of the image here. This function that the bootloader entered was at the very end. It had some no ops, which I'm assuming was for like flash caching reasons or for like turning something on and off in hardware. And then it jumps over here. Oh, I don't want this to be a function chunk. It is super annoying to disconnect function chunks from the function they're a part of in this version of IDA. I'm not going to worry about that right now. So there's some stuff down here. It's unclear whether this is data or code. That doesn't really look like good code. Could it be a 16-bit data tail? I don't know. So there's something kind of unknown here. And then a bunch of zeros. I'm going to collapse all these zeros right here. Can I turn this into an array? Okay, that's unused space. Okay, so that takes up all the space up until we hit this, which I think was the default parameter block. Guess this would be another array of 128. Default parameter block. The addresses are looking good so far. So I think this is more unused space. Great. So who's using this? Default parameter block. This function has a bunch of references to it, and then this one has one. Let's take a look at the small one first. What is this function like? This is a comparison with, what is this number? A151 or 41? Yeah, what is that? And this is probably hardware. Can we just look this up in the STM32 manual? For so memory map. Starts 4001 and 2C20. That is a timer. I wonder if this is an IRQ. Ooh, big old jump table. I wonder if this is processing commands out of a buffer. That would be convenient. So something timer related, maybe processing commands, maybe. It seems to be passing the default param block as an argument to some of these other functions. The loop structure is interesting. So thinking about what it might do with the default parameter blocks, obviously it might copy them somewhere. It might also be using them as like a fallback layer so that perhaps there's a function that gets the current parameter and it does a bunch of stuff, but then it has like a default of reading that memory block perhaps. Let's keep thinking about this and go back to the other place that we saw. That was this function. Ooh, this function's complicated. Neat. It's a flash offset. Oh. That's an offset to something that is not yet in Flash. So this might be something related to managing the saved data in Flash. I wonder why we're adding 2 here. Is there like a 0-based versus 1-based indexing thing going on? This function might be useful to figure out. Huh. This is weird. What is this hardware unit? Is this like something, some kind of write key for Flash? Let's get this a little more on screen. These are like magic numbers, which seem like either they're trying to make something obscure or it's something that's intending not to accidentally write to Flash. So 4002. $2004. Yeah, flash memory interface. I search for that address. I don't know if you can just search for the address. A lot of times they'll give it relative to something else. Let's just look in the table of contents for the Flash interface. Ah, is this it? No, this is for external memories. Yeah, this is for external memories, I think. Ah, I guess it's way up here in the memory and bus architecture. 4002200. Yep, flash key register. This is all seeming right. This is all like common tropes that you see in different micros. You just have to go like remember how it works on the particular microcontroller you're on. Oh. Is this not a complete document? Because this only has these couple of mentions to the flash key register. Now it's just the question of like figuring out which document I'm supposed to be in. The programming manual, is this the one? Yeah, so this verifies the hunch that we were trying to verify, that this is the flash unlocking routine. Cool. Flash write unlock. That's called by a few places. So we have B6. So this is a good starting point then. If we know this is how it's writing to the parameter flash, we can follow that back up to find how default parameters work and maybe how the actual serial interface works. Oh yeah, sorry, I was not looking at the chat as much as I should be. Okay, so we've got a few of these. BB60, B64, B794. Let's take a look at this one first, B64. This is a loop count. OX400. So then one thing I'll often do when I have like a group of related functions that I haven't understood the relationship between yet is I'll just start giving them names that aren't really very descriptive, but are at least better than sub. So I'm going to call these flash write, but include the address still so I can tell them apart. And anything that calls flash write unlock, I'm going to give it an address like that. Now I can actually go back to the default param block, and I can see, oh, it's being used by these two flash write functions. This timer might be like a deadline for the write to complete, perhaps. You know, I wonder if this is something about saving the settings and if there's an option to save. Well, I don't know. What does this go to? Oh, does this take some other parameters? Oh, maybe this is actually a flash write. No? No, that's just the unlock sequence. This R4 is where... So I was tracing this register, it goes from R9 to R4, and then it's actually preserved through this function call, so that's a parameter for this function, which might be another piece of the flash write. Let's see what that does. Oh. What's that register? 2200C. Flash SR. So this just writes to the SR register. What does the SR register do? It sounds like status, but I don't know why you'd write to a status register. It says status register. So there is a busy bit in there that we're supposed to check. There we go. There's busy, there's error bits, so maybe this is just clearing the error flags. Three, 5. Oh, this is write 1 to clear. Gotcha. This is clearing these error flags, and that doesn't really match up. I don't know why they'd be writing 3.5 to that. That would indicate this reserve bit is set, which is weird, and that they're only clearing some of these flags. Am I sure this is the right register? That looks like Flash SR. Okay. That's a weird thing to be doing to Flash SR, but maybe that's just how they're resetting the flags they care about. Huh, this is another hardware thing. That is the watchdog timer. Which apparently you have to reset by writing a key to. Which makes sense. Yeah. This is resetting the watchdog timer, which is not surprisingly something you'd have to call during the flash, right? This might also tell us where the main loop is, though. You can have a watchdog reset by itself or a decorated watchdog reset. Was this the only other place the watchdog reset is called? It's just all this flash write stuff, and then, yeah, 2 calls in this function. So this is going to have to be something that's called pretty frequently. And this looks like an infinite loop, so I assume this is the main loop. We might have just found main. Let's see what the path is between this and the entry point. Ooh, there's a flash right near the beginning here. Maybe something that looks for... If we were going to find something that takes care of initializing default parameters, this is probably where we'd find it. So that might be something really good to look at later. I'm going to first verify this is actually main. Yeah, that's main. Cool. That is very main. What is this? This gets called before main. It's like memory initialization. Just going to call this pre-main init right now before we know exactly what's in there. I assume this is just going to look like initialize RAM, initialize the clock speed, and stuff like that. This is just startup code that you would probably find in the tool chain. This is probably the clock initialization. So then in main, we've got a bunch of setup, a bunch of optional setup. So this is the main loop right here, I'm assuming. I wonder if this is going to be the motor on-off control. Like, if the motors are off, it goes one way. If they're on, it runs a bunch of additional steps. This is a 1 byte value. What is R4? That does seem to be some kind of parameter block. Neat. I don't think that's related to the parameters we've been dealing with elsewhere, so I think I'm going to call this something different. I'm just going to call it main flags. How big is this? Probably overlaps with some of these other references. It might be useful to try to find some markers indicating the serial commands. But I think we have many ways to get there at this point. Like, we could just keep pulling on threads related to those flash writes. Oh yeah, Dr. Toon says something very true. Man, I love IDA, but it's such an addictive time sink. Once you get stuck in and annotate standard C funcs and find some stuff, it's really hard to tear yourself away because it just keeps getting easier and more rewarding. Yeah, totally. I feel like reverse engineering is one of those things that, like, the more you find, the more fun it is, because you start to see the boundaries of the little world you're discovering. It's really nice. These are all pretty close together, so maybe there's some really little functions here. Oh yeah, these are little hardware accessors of some kind. I just want a register map. Oh, this is more watchdog stuff. Huh. I guess I need to maybe understand slightly more about how the watchdog timer works if I'm going to figure out this code, which I don't have to, but might as well. So the thing we saw before was the watchdog being reset. That was writing this AAAA key to this part of the register, which is just something that they designed this so that it's hard to do this by accident. So there are different keys you can write to start the watchdog, to allow you to access the settings, or to reset it. And this is this also the key register? Yeah. Why is this just another watchdog? Yeah, so that's watchdog reset, but does anyone call this? Why? 5555 from way back there. Yeah, this is how you access these other two registers, PR and RLR. Maybe this is something they use to shut off the watchdog intentionally. Yeah, and these are writing to the other two watchdog registers. Just prescaler and then reload. What did I just do to this? This doesn't seem like a good idea. Okay, I don't really care that much what this is, but it's weird that they would be resetting the watchdog to that degree in the main loop. That's usually something you would only want in your initialization code. Oh. This is setting interrupt priorities. Maybe this is not the main loop. Maybe this is like a loop around the main loop. This is like more optimized thumb code than I'm used to. I'm not sure what that does. Oh. Oh, this is restoring. Sorry. Restore interrupts, and this is probably clear interrupts. Okay, what about the flash stuff? So flash rates. These are the 3 flash write functions we have. This is the one with the timer, the unlock, ooh, clearing interrupts. What are you? This looks like a standard library function. I just need to figure out which one it is. This, like a CRC or something. Oh, I don't know how much I care about this function. Oh. I think this might be a CRC. Is this a CRC table? I'm going to guess that this is a CRC. I'm not going to spend too much more time on this. Here's a loop with a watchdog reset inside. 2 functions here. This is maybe like an unaligned memory copy. Hey, Tuco. Oh, Mike Batiste is pointing me toward the UARTs. Hey, little cat. Yeah, we could look at the UART. but I probably has been spending enough time in the flash memory. Yeah, it would be nice to map this back to the serial protocol, wouldn't it? So let's just see if I can find a UART control register. Would that be the first one? Clear interrupts, restore interrupts. Okay. I'm going to assume this is initialization. This seems more generic. What is this, like a pick a UART function? Yeah, this is picking a UART. Who calls this? Okay, there's 38. Or there's still USART 1. Hey, Tuco, what do you want, little cat? You're so chirpy. This, what is that? 4,000, 4,800. Oh, I really need a separate window just for the memory map. USART 3. Total guess about that. Serial 3 in it. Interesting. I wonder if this is the incoming serial port and the one down here is the outgoing serial port, and it's conditionally... I mean, this isn't conditional though, it's just later. What is this? This would be a really nice time to have a memory map of this processor that I could just load into IDA. This is reset control. APB2 enable. So, hardware initialization. I want to know where the data goes. We might just look for the data register unless it's hidden under some other abstraction. is this? 401, 3800. Yeah, that's it. Data register is offset 4. What does this pick a UART function actually do? The input so you pass in a base address to a UART, and this is just doing a bunch of comparisons. If it finds one that's equal, we're doing UART specific initialization, it looks like. It's just calling this function twice with different arguments. And this is modifying some hardware setting. This might just be hardware specific UART enabling. What is this? 4002. Okay, that's like a reset control. I think this is going to be reset serial port. So first thing, let's just see if anybody's referring directly to the data register. If not, we'll just assume it'll be this plus 4. So serial init. Oh right, I forgot the plus 4. Ooh, that's the data register. I guess we're saving it for later. Let's try to find some contextual clues. This is still setting up the serial port. I would assume that this is setting this aside for later for some kind of generic FIFO contraption to move bits back and forth in between. Like they might have some C++ or C abstraction that represents one of these serial ports, but then they have to initialize it by giving it all these pointers, which would be a little weird since they could just give it the base address. So R1 is a pointer to the data. It's like a pointer to the data register. Like R0 is already the data register address, but then we're storing that somewhere on the stack and then calculating the address of it in R1. Which goes down here to this sub. And this is initialization still, it's just shared between serial ports. Maybe it would be more instructive to look at the UART and find the region of memory it's storing this in, although that would probably be set up earlier. Ow, Tuco. Jeez. I'm like behind in the chat a little bit. So where would we expect to see the UART vectors? So the USARTs start at D4. We have USART 1, 2, 3. And I think we're probably using 1 and 3, but we'll see. So D4. And it would be nice to have some context here too. Okay, CC should be SPI1. I'm just going to copy a few of these in there so we have a reference point. Shh, to go. I hear you, Tuco. That's the cystic timer, which could be pretty handy. DMA1 channel 2. DMA1 channel 4. Tuco, what do you want, little guy? I think the cat might be hungry. 88. ADC1. I wonder what it's using that for. That's ADC1 and 2, actually, so we'll just call it ADC ISR. 98. This is CAN. What is in there? I wonder if there's a version of this that supports CAN bus. This is external interrupt. timer 1, timer 1 capture. Oh, I got USR 1 and 3. F4. This one's reserved. Huh. Oh, 1, 3 COO. This is ADC3? Huh. Looks like time 8. Two more, 118 and 11C. Time 6 and time 7. Lots of timers. Some of these timers probably go directly to motor control code. Well, maybe through some ST abstraction. Huh. That doesn't really do much. Maybe that's just ignoring that. Anyway, let's look at the serial ports. So we have SPI, maybe CAN, and the 2 US arts. Huh. That's interesting. Ready to go. Critical section over here. I'm guessing it's storing stuff in a FIFO. Is this the address we prepared earlier that points to the data register, maybe? No, that doesn't make sense. Oh, maybe it does, because it is a... I was expecting it to be a byte wide, but it would be a word wide. But... Maybe that's the data register. So this is a pointer to the result data structure. That'll be the serial 1 FIFO. Let's see if we can give this other one a similar treatment. So there's a second level of ISR, and then, yeah, this is the same data structure. Serial 3 FIFO. So the serial 1 FIFO is used in the serial 1 init, in the ISR, and then maybe this is part of what we're looking for down here. Serial 1 FIFO. Oops. Looks like we're reading bytes out of the FIFO here. So this function is only called in the main loop, or in main rather. It's called twice, serial 1 FIFO read. So maybe this is where the commands are coming from. We have one here. Oh, and one right down here. So where does the result go? I think that's the byte. Okay, so this is actually like a polling function, and it sends the results right here. Serial 1 handle read. Serial 1 poll, maybe. Ooh, is this going to be their serial state machine? R0 has a byte. So yeah, this might be the current state. Let's try that. Oh, Tuco, what do you want, little dude? I think he wants to go outside, but it's kind of late for that when I'm streaming. Okay, so the byte ends up in R5. Oh man, this is totally the protocol state machine. There's the 5A. Do we have a state 0? Yeah, there's the A5. So this is the default state and is looking for the A5. Oh, where does this go? This is like the part that I need a much bigger monitor for. Oh man, A5, 5A. Is this the output? So there's a lot that this could lead to. So I already am pretty sure there's some kind of buffer overflow in this. So it might be interesting just to get access to write to the RAM. But I think mostly I'm interested in going one level past this and trying to find the code that handles commands. So this is just handling the framing of the entire packet. what I would expect is that it would kind of pump the state machine through every time it gets a byte in the packet until it knows how many bytes are there, and then maybe it starts storing them somewhere. So I wanted to start with just maybe this is easier without the graph. So jump table. Okay, case 0, this is going to be the default case. So if it's not an A5, oh, you know what? Maybe that other packet framing where the packets start with like AA or whatever that was, maybe that's only interpreted by the bootloader. Maybe the actual firmware proper only knows about the packets that start with A5. That would make sense. Because if it doesn't see A5 here, it's just going right back to the default case. So the firmware is only looking for that one kind of packet. And then I assume we're just going to enter a different state now. Yeah, we're just incrementing the state. Okay. Increment, thanks. So then we're in state 1, we're looking for 5A, cool. So we've got the whole header. Then we're going to be in state 2, which should be looking for the target microcontroller. Current state. Ah, this is just storing serial 1 target MCU. Okay. And we're also reinitializing something here. This is a little non-specific, but sure. And that's just something else later. I'm not going to worry about that. Shh, Tuco, you're so hard to concentrate with, honey. Oh, he wants to play Bolt. Okay, anyway, case 3. Oh, Tuco. Reversing is easier when there's not a cat. But the cat is pretty awesome. And he's why I'm doing all this anyway, theoretically. So, store the target MCU, store the current command. Then case 4 should be the length. Hello, case 4. Oh, all of these are, I guess, the same. Cases 4, 7, 9. 8 to go. Mike is wondering if I could get an updated license from Hexrays since I'm providing all this training. Yeah, maybe. Okay, so we've got cases for 0 and 1, which are the header, 2 and 3, which are the target and the command. Then 4 ends up here in the default case. Is Okay, so maybe we don't care about the size immediately. So what about 5? 5 is like the first byte after we've got the size. Oh, there are multiple switch statements here. Okay, I need to take a brief restroom break. I think cat cam in the meantime. If you can even find him. Tuco, where are you? Tuco? I gotta pee. Maybe you want some food. Is that what you want? Do you want food? I think Tuco is hungry. I think he wanted a food. Oh, I guess Peter likes my suggestion about making a video about Tuco and why he's a great cat. Yeah, I'm definitely gonna do that. I think that's how I'm introducing this project. I'm starting to figure out how to edit this together into a video series, which there's always a huge lag between doing the thing and having the finished video about it, the way I do it, at least. But I'm starting to at least figure out how to make the first part of this into a video. Aw. Peter's also curious if there's any chance of a Tuco sibling or offspring. I don't know about Tuco siblings. Tuco was without his means of reproduction when he and I first met, so I don't know. Don't know if he has any siblings or other family that I could get in touch with. Don't really know super much about where he came from. I mean, I know he. So the person I adopted him from someone else who's like kind of an acquaintance, and I like kind of know them, but I don't really know that much about them. And I think he came here from Texas, but I don't know where in Texas or like what his home was like before he came here. Okay, so defaults. Maybe this is easier without the graph. So we have a jump table here. Oh. This is a weird jump table. How does this work? I assume the .w means that these are actually words, but maybe not. So these are some high states, like, I'm just a little confused with how this is going, because I expected it to go from, you know, some... Oh, okay. I think I'm just getting myself confused because there are two different switch statements here, and when I switch back and forth between views, sometimes I'm looking at the wrong one. So this is the one I want right now. This is the state switch statement. I think the next one might actually be the command switch statement, which is cool, but I'm not quite ready for that one yet. So I just want to get all the information I can from this case switch statement first. So 0, 1, 2, 3. 3 is the command. Okay, 4. This is what I want. This is where we're getting size and beyond. So I think this is the command size right here. Serial 1 payload size. And I'm assuming maybe this is how much of the payload we've downloaded so far. Payload offset, we'll say. And this is also a copy of the size. Is this just going to read bytes from the serial port directly into memory? Because that would explain our buffer overflow before. This is the data structure here, and it looks like at this offset we might just be reading that number of bytes, because this is the count. I think this is just going to be a loop that reads bytes. Yeah. So 18A is the offset to the actual payload buffer. Huh. This is the code that handles the target MCU. So it stores the target MCU. We're also calculating an address of the payload buffer before we've even got it yet, before we have the payload. And oh, okay, so we're just zeroing out the beginning of the payload buffer. Maybe they're checking it later and they don't want spurious stuff left in there. Okay, so 18A, we can probably find command-specific stuff later. It looks like we're going to find a bunch of instances of that. So I was actually expecting this to be a totally byte-wise state machine, but it looks like they just ignore the state machine entirely and just sit in a loop reading bytes once they get to the payload portion. So I don't know, that's weird. Like, what does this do when the bytes aren't ready? Like, this couldn't be completely blocking, could it? So R0 is the destination here. Oh, maybe this isn't the read loop. Maybe this is calculating something. This is reading 16 bits from the dest. Modifying it. Oh, maybe it's like shifting in a byte. Oh, I bet this is the CRC That would make sense. This is, yeah, that would make a lot of sense. So packet CRC init. Packet CRC update. So it's storing the command. And updating the CRC. Okay, so 4, we're storing the size and updating the CRC. Okay. Now can we get to 5? Okay. So we're updating the CRC. Then, okay, cool. That was a false alarm. This is totally a normal state machine. That was not a read loop, that was just a CRC update. So I think it's just going to be updating this by 1 every time it, yeah, here it is, next byte. So this is a state machine that just gets pumped by 1 byte, and this should be storing the byte. Why? Okay, so, I mean, so this is apparently the cap on the payload length. It'll only read up to 128 bytes, I think. Or maybe 128 words. It's gotta be bytes. So it's only gonna do this if we're in range. We're adding, what is this doing? 4 is our parameter structure. 0 is the offset, so R1. Oh, maybe the payload gets written at the beginning of the structure? Oh, or maybe the payload offset is 100. That would make sense. I just don't know. strb.w. I don't know what the .w suffix is there on a strb. But sure. So anyway, this is what we want. This is storing a byte to a buffer which is at, so this thing that we've been referencing based on R4 is some kind of serial FIFO data structure. And the thing that we're storing the packet data into is 256 bytes past that. So that seems fine. And we're just going to update payload offset, payload size. And then once we're finished, we go to the next state, which is state 6, which is right here. And we just ignore this, and this is probably going to store partial CRC. Serial 1, incoming CRC. And then I would expect the next state, 7, to, I assume this code increments the state. Oh, that's just setting the state directly. Okay. So yeah, this is just going to the next state. This is storing part of a CRC. Then I think this should be finishing up the packet. So R5 here is going to have the second half of the CRC. Here we are combining it with the rest of the CRC. And so now this is actually the incoming CRC as it says it should be. We're comparing it with the calculated CRC. Ignoring the whole packet if there's a CRC mismatch. And if there's not, we're loading the target MCU and the command. Ooh, is this the destination? What is this 3? We're checking to see if the target is 3. That's interesting, because 3 is normally the computer. Maybe it ignores things specifically if they're 3. Yeah. Interesting. This is, where's this going? If the target is not 3, it's going here. We're going to have 2 different... I'm expecting that this is going to be related to how it decides whether to pass on commands to the other microcontrollers or not. It's just weird that they would be doing this right here. And usually 3 indicates that it's like no regular MCU, or it's like the computer that's controlling it. That's what 3 usually means. So this is where it goes for like a normal packet. But this is where it goes for a target 3 packet. So, target 3, what does it care about in target 3? Do I want to go, this is a crossroads, I could go here or I could go there. And what is it even looking at? I assume it's looking at the command. Yeah, R1 is the command. This might be interesting, but let's take the other path first. Let's see what it looks like over here when the target is not 3. So we're taking the size. Extending it. This might be an incoming command handler. So this is the payload buffer. And this is getting ready to leave the function. This is making a tail call to a different function. So, at least I think that's what's going on. So R3 is going to be the size, sign extended. R2 is the buffer. That would mean R0 and 1 are being reused, I assume. From up here? Okay, so 0 and 1 are still the target and the command. So this handles a packet. I think maybe what's going on is that this has a built-in switch statement for commands that are destined for target 3, so those might be special. Those might be interesting to look at. But I think the normal commands go here. And so let's get these parameters right. And we've got R0 is target, R1 is command, R2 I think was payload, and R3 is size, but let me double check that. I might have gotten those last two backwards. Yeah, I think that's right. Okay, serial 1, handle packet. What else do we got? This is pretty small, actually. I was expecting this to be like a switch statement. I wonder if I got these backwards somehow. Is this some kind of mutex? Yeah. Let's call that a busy flag, maybe. Command is R1. I don't think we're in serial 1 anymore. I think we're in a different object. Because it's storing another copy of this stuff, like the command is going to this data structure now. This is R6. I'm just going to call this packet in. Packet in busy. This will be packet in command. Target. Oh, here's the A55A again. Maybe this is some compatibility layer, like they had something designed to just get like a fully formed packet buffer, but then they need to copy the payload into that from the state machine. That's the size. And so I assume this is going to leave this in the buffer for something else to process. Let's see who else uses that command that we just stored. Oh, we have two stores to that, but nobody loading from it. That's probably something we're missing then. This is something else that's submitting packets to the same place, it looks like. Where is this called? From main and from something else? So is this like a way to send packets synthetically? Command B? What was command B? Oh, that was for the handshake for initializing PC control. Yeah, I wonder if this is related to determining whether the startup mode is PWM or serial. I mean, I'm still curious what this whole switch statement is down here, because I would have expected this to be the opposite of the way it is. So maybe am I getting this wrong? Oh, I think I am. Ah, yes. That makes more sense. That's right. This is not a comparison. This is a bitwise AND. So I'm getting distracted by other stuff in chat. Yeah, so this actually mirrors some behavior I was seeing before, where if I was trying to figure out which microcontroller targets work, and it seemed like it was just looking at the low 2 bits and ignoring the rest. So maybe this is actually just checking, is this for me or is this for the other microcontrollers? Because if so, I'm reversing microcontroller 0 right now, so it would make sense for this to be hard-coded just to check, is this 0? So, is this me? Yeah. So, I'm going to call this got foreign packet, because this is a packet that's designed for someone else, but I got it. So this is actually probably related to read broadcasting a packet that's designed for someone else. Handle foreign packet. Okay, that makes a lot more sense. I thought that logic looked backwards, and this explains why it was. So now this is receiving a local packet. "14 cases." So let's just go right to something that that we might care about. Let's do like getting commands, because a get will tell us how it replies. It'll also tell us where the commands or where the parameters are stored. So the get command is command 6. And this is operating directly on there. This might be our getter. What is this? What is this thing? Well, I'm not sure what those are. I'm going to see if I can ignore those for now. So we're getting some stuff that I don't know. Then there's loop. This looks like another mutex. Well, spin lock. They've got something they're trying to keep this and the IRQs from interacting badly over. So this is probably some kind of parameter mutex. And then, is this building a reply? This looks like a reply header. It's just storing that directly to R4. Yeah, I'm assuming that's some temporary space that we're building our apply in. All right. There's some variables and stuff later on, but I guess the beginning of that structure, this looks like it'd be really easy to buffer overflow, because all the interesting data seems to be after the payload buffer, like immediately after. Anyways, we're building a reply header. This is a get response. So this is the command. I'd expect to see the microcontroller target also being set here, but maybe that happens elsewhere. So this is the command number. This is the payload size. This is a pointer to the payload. Oh, is it? Payload size. Oh yeah, we're just loading and storing in 2 chunks because it might not be aligned. So that's the parameter result. Did we just call a function that we might have grabbed that from? Where would R0 be here? Because it looks like we already have the result. Yep, this must be the parameter base. All right, I guess those are just stored in RAM. Param RAM. Cool. I wonder if I can mash this up with my memory dump. 24C should be where the parameters start. And it looks like they're just one-to-one mapped, which means I would expect to see the version and stuff here in the RAM dump. Unless I just wasn't in a state where that stuff would have been initialized. 24C. This is a RAM dump I made earlier when I had the debugger attached. We couldn't read Flash, but we could read RAM. That might be it. That's the version at the end. Yeah, I think that's the parameter space. Why didn't I see this earlier? It's closer to the bottom of memory than I expected it to be. It might even be on the stack. I mean, it couldn't be on the stack, though. It's statically allocated here. Where does the stack even start? Oh, stack is way up here. Cool. It's like not really at the beginning or the end of RAM. It's just kind of somewhere. So now that we know where the params are in RAM, we could actually take anything we don't know about and try to match it up to this area. We could also try to find out whether there's... So we know that there's no active code really in the reading. So reading a parameter doesn't have any way to affect it. It's just grabbing something from RAM. And that's really good to know. It might also be nice to know whether writing parameters works the same way. So, serial handle read. Okay, so this whole thing, serial handle read, 2 switch statements. There's one for cases up here, and then one for commands down here. And so we were just over in 6, which is command read, or parameter read. So command set is 8. Oh, that's right. Command 7 is still kind of unknown. We didn't really figure out what this one did. Well, we have a better idea of how to figure out the commands now, because we can just read the code. This switch statement maps directly to these commands now, which is pretty nice. So command 8. Oh, command 8 is really little. Command 8 also had the unknown byte. So... yeah, this is the 1 byte parameter. Payload buffer is at this 100 offset. This is not actually an address, this is just an offset. So, oh, it's not an extra byte, it's a 16-bit parameter. Why do we have the ability to set with 16 bits of reach? That seems like a bad idea, unless they're truncating it, which I don't think they are. Yeah, there's just, this just goes straight to memory. So this command is very dangerous. This just writes to RAM starting at the location there, but you could easily just like splat whatever you wanted later on in RAM. So any experiment I did where I set that second byte of this packet to a non-zero value would have just written stuff elsewhere in RAM, and that could have easily caused the crash that I ended up having. Well, that's simpler than I expected it to be. So any other interesting commands? So command 8. I'm going to rename these poke and peek, because they're about that powerful. What about command 7? I'm curious about that. There's a bunch of stuff here. Oh, is command 5, I think that was our flash save. Yeah. Looks like the key has to be external. That's interesting. This might be for sending back a response. Yeah. Let's see if this is a shared function for sending responses back. maybe. What about this one? Oh. Huh. This might be pulling until the write is finished. Oh no, this is putting together a response. And does that go here? B506? Yeah, cool. Whoa. So I'm going to call that serial 1 response send, and this one will be command 05 response send, or just command 05 response. And this I'm going to call flash write command 05, or command 05 flash write. What else? Command 3 was the motor on off. We're right here. So that's the argument. Looks like we're testing. Testing its oneness. Yeah. Call that motor on-off state. It's used in a bunch of places. Cool. So we have command 3, command 5, command 6, command 8. This is command 11. Do we know anything about command 11? That's the initialization handshake. This is what the PC or whatever is on the serial link sends in order to break the normal initialization sequence. Whoa, another jump table. Oh, no, that's just the repeated comment. Never mind. PC init. So this is just checking to make sure the parameter is 1. This just has no effect unless the parameter is 1. And it's just setting a flag right here. I kind of want specifically this byte, not the entire structure. Call that main flag PC attached. Case 12, that is undocumented currently. That's command C. Currently unknown. Oh, that's doing something else with parameter RAM. Command C. It's just copying from this value to that value. Copying 58 to 9A. These are going to be different from the numbers I've been using because these are byte offsets. Let's just keep these in offset for now. Oh, and this is using the same response as command 5. let's just call that command response. Okay, so C is something to do with copying parameters from one place to another. Probably not super interesting. Case 16, aka command 10. Haven't seen this command at all either. This would have been command 10 in hex. Writes a byte from the parameter to this variable. Interesting. Well, there's nothing like super surprising in here. In fact, there aren't really that many commands total, but I suspect if we looked at the other serial port, we might find a version of this that supports more commands. It's also true, probably, that like, I know that I can send commands that the other microcontrollers pick up that this one doesn't have to know about. Like, I can send command 1, which is usually what PWM messages turn into. I can send that to the first micro, and it'll pass it on to the next one, even though it's not handling it right here. All right, I'm getting a little tired, but I'm going to make sure I check up on chat and get anything I missed and answer questions before I wrap this up. And maybe play with Tuco a little bit. Del Gato Stream Deck. Oh, that's cute. I actually just got one, not quite like that, but ended up getting this thing from X Keys. It's that thing with 16 buttons. So, for example, you know, pretty much like that. That's been working pretty well. Nice. Oh, Michael, I totally appreciate the block analysis. That was super helpful. But yeah, it was, we just randomly found the key in the RAM dump. Specifically, MakeOMK was the one who found the key, and Robert was also looking at it and found some useful stuff. Oh, and Mike is asking why IDA does that word relative to whatever. This is because it was assuming it was an offset. So there's a thing that some compilers do where they're actually trying to refer to a variable at a particular place. Like you might have actually compiled this with a variable at this offset, but then it has a register that's used as a common base address for several other things. And it's a super common optimization, especially in ARM. So the compiler will just set R4 to something kind of arbitrary. Then IDA will go back and figure out, okay, R4 is set to this, and so it propagates it through. And so sometimes that's useful, but I don't know if it's operating in a useful way right now. Since I think R4 came... Yeah, so see, it knows what R4 is since we set it to a constant up here. So it can just represent these differently. Like, we can represent these as a numeric offset from R4, but that's not as useful. It's more useful to represent it as a symbolic offset from this base address. So that's what it's doing here. It's usually what you want. But... yeah, like down here, it may or may not be. But that's interesting. That means that the command payload buffer is like literally like right at the beginning of RAM. Well, I guess that's the buffer for outgoing commands. I think the incoming commands are at 256 bytes later, but It's still pretty straightforward. So okay, this right here, and just in case anyone's playing along at home, I've been calling this one serial 1 handle read. It is at 800A708. Yeah. Or sorry, that was where it was currently. The function itself is at 800A62C. And so this handles, this is called with a byte in R0. There's a FIFO buffer in between this and the actual serial port, but this is still called pretty much once per byte coming in on the main serial port. So, and then there's a state machine which handles depacketization, and then there's a state machine which handles individual packet types, or a switch statement for packet types, rather. And I think one of the more interesting revelations from this so far is, despite there not being obvious, like super powerful, undocumented commands here, the plain old parameter get and set are pretty much unbounded. Like the set actually has a 16-bit parameter number that they don't bother bounds checking. And the get has a 8-bit parameter that they don't bother bounds checking, but that's less exciting. So we could just totally start storing our own stuff in RAM. I wonder if they did that intentionally, like if they wanted to reach a 64K chunk of RAM for some reason. It seems much more likely that they just set their struct member to be UN16 and didn't really think about bounds checking. So these are the actual commands. And this param RAM buffer is exactly what they're writing to. So some of these references to param RAM might be this entire thing as a block. Some of them might be the first word in it specifically, which I don't know the meaning of. So cross-references to this, we're going to see a mix of those two. But cross-references to these other members, we'll probably see something that's specific to just that one member, which will be nice. So I'm curious if we can find anything for the version, which is like the end of this. So 24C, we would expect to see that right before 34C. So this would be param 7F, I think, version. Oh, it copies that from the default parameter block. Neat. This is where it sets the version. Interesting. And so this is another flash write related function. Where does this one get called? This is in main. Flash write on startup. So if there's anything that just fixes the parameters, I would expect it to live here, although I don't know that something like that would exist. But definitely a few references to the default parameter block and the parameters proper. And the watchdog timer. Oh, US Water Rockets is seeing the Kitten Academy stream recommended. It's a good stream. I like that one. Maybe it's recommending it to you because I like it. You never know. Well, I'm running out of steam for just like barreling through this. There's plenty that's interesting in here though. Like we could take any parameter that we're interested in and just dig through here to try to figure out what it actually does. So like 0 might be an interesting param to know about. Some of this stuff probably only appears in the other firmware. Oh, this is something that might be interesting to know. This 6.7, the Windows software sets this to 1 right after power on, and I've been doing the same thing in my own motor power on function, but I don't actually know what this does yet. We could also look at the heading follow code, since we know where that one lives. You know, we could try to figure out what it's doing with a particular sensor, since we know where the sensors are in the parameter space. We could try to figure out what 4D is, because we've been kind of confused about that one. There were these two things that we were trying to tune. 4D seemed to be related to gains or centers somehow. And 6.4 seemed to be related to motor phase calibration. Both of those would be pretty interesting. Let's take a look at 4D and see what's there. So we'd calculate the address. So it starts at 24C. Parameter is 4D. Each parameter is 2 bytes long. To E6. So this will be parameter 4D unknown. Oh. Something over here in serial 1 handle read is writing to it. Huh. That unknown command 12 is dealing with this thing. So this is actually writing to command 4D. Maybe this is for capturing a center. What do we got over here? 2A4. Copying, this is param 2C. Do we know what param 2C is? Oh, and it looks like it can store it in one of 2 different places. I wonder if these are 2 different stored values depending on like what orientation the gimbal is in. Do we know anything about 2C? Magnetic sensor angles. Well, geez. Because I thought that that might have been just the center in magnetic units, but maybe it's not. Huh. The reason I'm confused is like this seemed like the obvious thing earlier, but then it seemed like maybe it was more complicated, and I guess I'm surprised to see that it's as simple as my original guess. Huh. So 2C would be the magnetic angle. I'm just going to call this angle, or mag angle. So center angle, maybe? Yeah. So Command OC should capture, and there's another path here which could be interesting. Let's investigate that too. So this is just checking whether the parameter byte is non-zero. Yeah, so if it's 0, we set this center angle. If it's 1, we set this. Otherwise, I assume we do nothing. Oh, we just send, this does send a response. Okay. Interesting that it would send a response even if the parameter was invalid. And where's this one going? 314. That's 64. So that's some kind of stored angle. 64, right? Huh. This is weird, because I thought this might have been in some other units, but it looks like this is also... So maybe the calibration just consists of Command C. But, I mean, we should have been able to achieve the same thing by setting these ourselves. Unless it just needs to happen, like, atomically, otherwise the control loop gets into a weird state. But that might be worth a try, just having... Because it looks like... My guess is that they have two different reference positions they need to store. Maybe one of them is related to the center that it's supposed to hold at, and the other one is related to like a mechanical center for the motors or something like that. Yeah, I'm right there with MakeOMK. What positions does it need to be calibrated in? So yeah, it looks like... I'm going to write... This is a stored angle for Command OC with parameter 1. I'm pretty sure that is the center. So I'm just going to call it that. And this is probably some kind of motor homing location, which we can experiment with. Anyway, I think this might be an actually good point to wrap up the stream. I don't want to get really deep into exploring these Command C permutations, since I think what looks like maybe what we need to do with this is, you know, assuming there aren't any other giant parameter problems, maybe what happens is you send this thing some default parameters, and then you hold it in specific positions, probably with the motors off, send it Command-C, store that, then turn on the motors, something along those lines. Oh yeah, I need a visible countdown until the next "we're still on" tweet. That's a good idea. Because yeah, otherwise I'm sure I'm gonna stop it right after that tweet goes on. Hey Tuco. Hey cat. Hey cat. What do you think, cat? Well, thanks for tuning in, everyone. Hope you enjoyed the combination of parameter UI fussing and firmware decrypted IDA exploration. I certainly enjoyed it, and this should be some interesting footage and hopefully some interesting gimbal protocols for us to use later. Oh, interesting. To really wrap up, go back to Fusion. I think I know what this does. I don't think this works anymore. Command Option Control Shift N. Oh! Wait a minute. This still works? I thought this got removed. Is this no longer in the VMX? Huh. Did they resurrect my Easter egg in a different form? Or is this just an old version of Fusion? Because I thought this Easter egg got killed. Oh. Yeah, here, let me, sorry, I had already started to wrap up the stream when I tried that. So, yeah, so I'm in VMware here, and it's holding down all the modifier keys and N for new VM, and then you get Pong OS. And it has the pride mode. Okay, how does this work? The way this worked when I first wrote it is that the UI gave the VM a 0-byte floppy disk image, and then this was actually included in the VMX. But maybe this works differently now? Where is this VM? Huh. Ooh. Oh. Oh, very nice. I think this might be the new location. Yes, that's it. Oh, I'm so happy this wasn't completely removed. So I originally wrote this such that it was like baked into the VM in a way that was kind of weird. And then I guess some folks at VMware, long after I left, got cranky about it and removed it, but I guess at some point it got back into the UI. That's really neat. So this directory is just full of all sorts of junk. So, and then sample.flop. Yeah, you know, I think we determined that this actually works under QEMU also. Oh, do I not have that installed here? Oh. That's probably going to take a while. Anyway. If you're curious about what's behind that, I actually put the source code up on GitHub recently. Is it Pong OS? No, egg. Yeah, if you just go to scanlime/egg, then I guess it's no longer dead. I guess I should fix that. But yeah, you can also run this under QEMU. I guess I don't have QEMU ARM installed on here. Anyway, I'll leave that as an exercise for the reader. I should avoid opening another can of worms right now. But if you don't have VMware, you could try it there. If you do have VMware, you could just press the key combination. And that is finally our wrap-up point for today. Are we missing the cat? Well, I guess I'll track down the cat on my own. So, thanks for tuning in. I will see you next time. Thanks for all the wonderful reversing tips. It's been fun doing this together. Happy hacking, everyone. Meow.